All right, both in the back and just one in the front. Is that what you got? Okay, so this video is trying to tell you, how is the size of an atom compared with objects that we understand, and how big are the pieces of that atom. So the first thing they said is you'd have to fill Earth with blueberries, right? How many blueberries do you think would fit inside our planet? That's a lot of blueberries. That's how many atoms, roughly, are going to be in a grapefruit. Well, let's zoom in on those individual atoms. So here is my atom, and here is my nucleus. How many of y'all have been to Nissan Stadium? It's a cool place, right? Now imagine a ball that would fill Nissan Stadium. That is the outside of your atom. And how big would the nucleus be? It would be a marble sitting on the 50-yard line in the dead center of Nissan Stadium. That's how small the nucleus is compared to the tiny atom. So you can see these parts are really, really, really tiny. Really tiny. Okay? Now let's go into some details specifically about the atom, and I'm going to show you how to do the only math we're going to do for this lesson. Okay. Here is an image of the atom that we're used to seeing. You've got your shells for the electrons, and you can see the nucleus. Obviously, this isn't to scale, right? Because that nucleus should be really, really, really tiny. So small that you wouldn't even be able to see it inside this circle. It's that small. So now let's look at how we're going to do what we're going to do today. You're going to want to write this down in your notes, guys. So every atom is going to have a couple of important things that are listed on your periodic table. Each element is going to have a box on the periodic table that looks like this. You're going to have, at the very top, is going to be a solid number. Yes, draw what I'm drawing and write what I'm writing. At the very top is a number. That is the atomic number. Now, do y'all remember which subatomic particle equals the atomic number? Protons, exactly. So that is the number of protons. You're supposed to draw the box, put a 6 at the top, write atomic number, protons. That's this right here. Now, underneath the atomic number, you're going to see something we call the symbol. That's like an abbreviation for that element. So C is for carbon. We are all carbon-based life forms, so I'm using carbon because it's important. Underneath the letter or symbol, you're going to see the name. And then below that, you're going to get something called the atomic mass. That tells you how heavy that element is. One atom, that's actually a mole of substance. But that is the weight or the mass of that atom. Okay? So we have the atomic number at the top, the symbol, the element, and the atomic mass. Now here's where the math comes in. Now on your assignment today, you're going to have to tell me how many protons, neutrons, or electrons are in any given atom of a specific element. So if I say, how many protons are in nitrogen, you've got to figure that out. Then I'm going to ask you, what's the mass? How do you find the number of neutrons or electrons? Let's do this. First thing, the number of protons is always going to equal your atomic number. Next up, the number of electrons, if I can write today, is always going to be the same as your number of protons. Because we said that all atoms are what? Neutral. So that means the positive charges have to equal the negative charges, right? So electrons, negative, are going to equal the positively charged protons. That way we get a zero charge. The next thing we got to do is figure out how we find out how many neutrons we have. Because neutrons don't have a charge. So I can't do a balancing act to find the neutrons. I got to do some simple math. So the math for that is going to be mass minus protons equals the number of neutrons. So let's look at carbon here. Carbon has a mass of 12. We're going to round it. It's got how many protons? 6. So how many neutrons? 6 neutrons. Now in this case, it works out nice and even. Sometimes, let's try fluorine. Fluorine's atomic number is 9, and its mass is 19. So for fluorine, we're going to take 19, and we're going to subtract 9. We actually have 1 extra neutron. They don't match sometimes. So be prepared for that. Always take the mass, subtract the number of protons. It will give you the neutrons. Does that make sense? It's not too difficult math, right? Crickets? Can you get a calculator? You're welcome to, right there. Please do. Now I'm going to hand out your assignment. You guys have got 25 minutes to do this. And before I let you loose, there's one thing on the back I want to show you. Can I get a volunteer? Kendrick, come on, bud. Kendrick's going to hand out your assignment. What I want you to do is flip over to the back page, because I want to do a couple of those with you, because we haven't really discussed a whole lot of that yet. And it has to do with those shells. The electron shells. So the models that Bohr gives us always look like this. I'm looking. Yes, that's it. Flip over to the back page of that. On the back page, you're going to have to draw something we call Bohr models. And I want to make sure you understand this. We've discussed it, and it was in your book, but I want to make sure that you've got a little bit of experience before I send you off on your own for this assignment. So what do we call these circles around the nucleus of this atom? They're shells, exactly. So write this down in your notes, or write it down on your assignment. That way you don't lose it, because I'm going to let you use your assignment as notes. So the shells, we have the nucleus in the center, but the next shell can hold 2 electrons. So I can have 1 here and 1 here. What about the next one? Does anyone remember how many it's supposed to hold? No, the first one's 2. 8. Look at that. Somebody was paying attention. The next shell, you get 8. Now here's where it gets a little funny. I've heard 2, 8, 16, 32. What I'm used to is 2, 8, 8, 16. And even then, it's not exact. It depends on the energy level. It gets complicated. So I'm going to keep it simple. Let's do 2, 8, and 8. That's going to cover 18 different elements, and we're not going to go any further than that. This is just an introduction. So 2 right here. Then you get 8 and 8. That brings us to the next point, the idea of valence electrons. So valence, spelt like this, V-A-L-E-N-C-E, electrons. These are really important because this tells us what these elements are going to react to, depending on how many valence electrons they have. So the valence electrons are the outermost electrons. So we call that the outermost shell. You're going to look for the number. So let's do carbon. Carbon's really popular. If it wasn't for carbon, we wouldn't be here. So we give it a lot of props. So carbon has 6 protons, it has 6 electrons, and it has 6 neutrons. So we're going to start off by just forgetting this and this. We don't need that. This model only concerns itself with the electrons. So we need to fill this up. We have 6 to work with. So we're going to start off. How many go in the first shell? 2. So let's draw our 2. So we've got 2. How many do we have left over? 4. So I'm going to put next shell. 1, 2, 3, 4. So how many valence electrons do we have? 4. That means carbon has 4 electrons, which is why it's so popular. It can give or take. It's the middle ground for most molecules. So the valence electrons on carbon equals 4. So if you look at your assignment, I just did one of them for you. I think it's number 6, right? So this is how you're going to do this homework. Fill the shells up step by step, 2, 8, and 8. And look at the outer ring. How many electrons do you have there? If it says, if you got 0, that means that ring doesn't exist. You only get the ring, the shell, if there's an electron in it. Does that make sense? Yeah? All right, so what I want you guys to do, this is a front and back assignment. Both sides will be due next time I see you. Let's get some practice in. And at the end of class, I've got a little announcement. All right? Yes, you may. All right, so stay tuned for more, guys.